Let's start with the basics of TensorFlow. It's basically a really awesome toolkit for doing all sorts of calculations, especially when it comes to machine learning and artificial intelligence. Think of it as a set of powerful tools that helps you build smart applications. What makes it special is its flexibility. You can write code just like regular Python, or use a more visual way of describing how the calculations should work. It's also incredibly efficient thanks to its graph-based execution system and automatic differentiation, which takes away some of the heavy lifting when training complex neural networks. Plus, because Google created it, it's designed to scale up really well, so you can use it for huge projects. Okay, let's talk about how TensorFlow stacks up against the deep learning frameworks. The big difference really comes down to how they handle computations. TensorFlow primarily uses something called static graphs. Think of it like building a detailed blueprint before you start constructing the model. PyTorch, on the other hand, uses dynamic graphs that builds the model as it runs, which makes debugging much easier and is often preferred by researchers who need flexibility. Keras is kind of a wrapper around TensorFlow or other backends. It's designed to make building models really simple and fast, perfect for getting started or quickly experimenting with different architectures. Okay, let's talk about tensors. In TensorFlow, they're the absolute bedrock of everything you do. Basically, they're multi-dimensional arrays, kind of like a spreadsheet that can be arranged in different ways. You'll see them used for all sorts of things, from simple lists of numbers 1D tensors to representing images as matrices or even volumes like videos. The key is understanding that they're flexible and can handle data with varying dimensions. Okay, let's talk about the heart of TensorFlow: computational graphs. Imagine a really detailed flowchart that outlines every calculation happening in your machine learning model. That's essentially what a graph is. Each step, like adding two numbers or applying an activation function, is represented as a node. These nodes are linked together with arrows, showing exactly how data flows from one operation to the next. The real magic here is that TensorFlow automatically figures out how to calculate gradients for you, which makes training your models way easier. And because it's all defined in this graph format, TensorFlow can also optimize things like merging operations and making sure everything runs smoothly on different devices. Okay, let's talk about TensorFlow sessions. In the older version of TensorFlow 1x, you absolutely had to create a session object. Think of it like telling TensorFlow, "Hey, I'm ready to run this graph now." It was all about explicitly defining your calculations and then starting the execution process within that session. You'd have to manage the creation, running, evaluation, and shutdown, which could get tricky, especially when debugging. Now, with TensorFlow 2x, things are much smoother thanks to eager execution. This runs operations immediately, just like you're used to in NumPy. Sessions are still around, but they aren't as necessary for everyday work. It makes debugging way simpler because you can see the results of your code right away, and graph mode is still there if you need it for performance. Okay, so let's talk about eager execution in TensorFlow. Previously, when you built a TensorFlow model, you first defined everything as a graph, essentially a blueprint for how the calculations would happen. Then, you'd actually run that graph. Eager execution is like saying, "Let's just run this code asterisk as asterisk." We write it, it executes operations immediately, so you can debug them like any other Python script. This makes development much more straightforward and intuitive because you don't have to wait until the very end to see if anything went wrong. Okay, let's talk about how to build a basic neural network in TensorFlow. We'll use Keras sequential model, which is great for creating linear stacks of layers. The first thing we do is import TensorFlow. Then, we create a sequential model using Keras. Sequential. Inside the model, we add layers one by one. Most commonly, you'll start with an input layer and some hidden layers. You can specify the number of nodes in each hidden layer and what kind of activation function to use, like ReLU for nonlinearity. Finally, you'll have an output layer that will give you a prediction. Okay, let's talk about the difference between TF variable and TF constant. Basically, TF variable is like a slider. You can change its value during training to adjust your model. It's tracked by TensorFlow and updated as part of the learning process. On the other hand, TF constant is just a fixed number, it doesn't change at all. It's like setting up an initial value that stays exactly the same throughout the entire computation. Both are important, but they serve very different purposes in building your TensorFlow models. Okay, let's talk about gradient tape. Think of it as TensorFlow's memory for calculations. It's a tool that keeps track of every asterisk operation you do inside a block, like when you're training a model or building a custom layer. It essentially records the steps so that later, if you need to calculate gradients, how changes in your inputs affect the output, gradient tape can use this recorded information to figure it out really efficiently. It's incredibly useful for things like creating your own training loops and designing more complex models. Okay, let's talk about how TensorFlow figures out derivatives. That's automatic differentiation. Essentially, it lets us automatically calculate gradients without having to write all those complex formulas ourselves. TensorFlow uses something called backpropagation, which is like tracing the steps of a calculation in reverse to find the slope at any point. It builds a graph of operations and then efficiently computes those gradients. The TF gradient tape is really key here. It's how you tell TensorFlow what parts of your code you want to calculate derivatives for, and the TF gradient function actually does the gradient calculation based on that tape. Let's talk about the difference between how TensorFlow trains models, specifically model fit versus creating a custom training loop. Model fit is really handy for getting started. It just takes your data and automatically handles all the steps involved in training, like feeding batches of data to the model, calculating how wrong it is lost, and adjusting its weights accordingly using an optimizer. It's super simple and perfect for standard problems. But sometimes you need more control. Maybe you want to track specific metrics beyond just loss, or implement a custom stopping strategy, or use a very specialized optimization technique. That's where custom training loop comes in. It gives you the power to define exactly what happens at each step of the training process, from loading your data all the way through calculating gradients and updating weights. It's more work to set up initially, but it unlocks a whole level of flexibility. Okay, let's talk about saving and reloading your TensorFlow models, a really important step for getting them into production or sharing your work. The easiest way to do this is using TF save model. This creates a structured directory containing everything you need: the model itself, its variables, and all the information it needs to run correctly. You can load this later with just a simple command. Alternatively, if you're working directly with Keras models, you can use TF Keras models save model. Just be mindful of custom objects. You might need to tell the loading process what they are using the custom object's argument. Finally, always keep in mind that TensorFlow versions matter. Make sure your saved model is compatible with the version you're using to load it. Okay, let's talk about checkpoints in TensorFlow. They're super important for saving your work. Basically, a checkpoint is just a snapshot of your model's current state during training. It captures all the learned weights and biases at that exact moment. If you stop training, maybe due to an interruption or because you want to try something different, you can pick up right where you left off by restoring from a checkpoint. You can also use checkpoints to compare how your model is improving over time, and even load the best performing version based on its validation loss. Okay, let's talk about callbacks in TensorFlow. They're a really powerful tool for customizing your training process. Think of them as little helpers that run at specific points, like after each epoch or when you save the model. You can write your own functions to monitor things, log metrics, and even decide if it's time to stop training early. The code snippet shows how to create a simple callback that prints information about each epoch. You can easily extend this to do much more complex actions, like saving checkpoints or adjusting learning rates. They're super useful for getting detailed insights into what your model is doing. Okay, so TensorBoard is like a visual dashboard for your TensorFlow projects. It's incredibly useful because it lets you watch how your model is learning as it trains. You can see exactly how your loss and accuracy are changing over time, super helpful for diagnosing problems early on. Plus, you can literally step inside the model itself and visualize its architecture, which can reveal unexpected issues or bottlenecks. It's also great for looking at the distribution of weights and activations to catch things like vanishing or exploding gradients. To use it, just run TensorBoard from your terminal, pointing it to the directory where you've saved all your training logs. Okay, let's talk about how you define your TensorFlow models. You have two main routes, the traditional method of subclassing and the more modern functional API. Subclassing is like building a model from scratch, inheriting from the base TF Keras model class and customizing everything yourself. It gives you ultimate control but can get complicated quickly, especially as your models grow larger. The functional API, on the other hand, is more like describing what asterisk you want your model to do, a graph of functions that take inputs and produce outputs. It's often easier for building complex architectures with multiple inputs or outputs and tends to lead to cleaner code. Okay, let's talk about getting your data ready for TensorFlow, a crucial first step. We primarily use the TF Data API, which is designed to make this process super efficient. First, you load your data. That could be text files, images from a directory, or anything else. Then, you'll likely need to do some preprocessing. This might involve normalizing pixel values like scaling them between 0 and 1, converting categorical variables into numbers using one-hot encoding, or breaking down text into individual words through tokenization. Don't forget that batching is important for training. It groups your data into batches for faster computation, and shuffling helps avoid bias in your model. Okay, let's talk about the TF Data API. It's a really important tool for working with TensorFlow models. Essentially, it provides a streamlined way to handle your data pipeline. Instead of having to manually load and process everything in Python before feeding it into your model, you can build this entire process directly within TensorFlow using the TF Data API. It's built on top of tensors, so it integrates seamlessly. The key is that it's incredibly efficient. It uses optimizations to run smoothly on GPU, and it's designed to handle huge datasets without needing everything in memory at once. You can easily read from different sources like CSV files or even NumPy arrays, and it lets you apply various transformations to your data as needed. Okay, let's talk about how TensorFlow efficiently handles your data. When building pipelines using TF Data, we need to consider batching and prefetching. Batching groups multiple elements of your dataset together before feeding them to the model. Think of it like sending a whole group of requests at once instead of one by one, which drastically cuts down on the number of times your model needs to be called. Then there's prefetching. This clever technique anticipates what's coming next and loads the data in advance, so when you're actually processing the current batch, the next batch is already ready. It's like a conveyor belt. The system never has to wait for data to arrive, it just keeps moving. Both of these techniques are critical for maximizing performance, especially with large datasets. Okay, let's talk about dealing with situations where one type of data is much rarer than others. It's super common in real-world datasets. Think fraud detection or identifying rare diseases. If you just train a model on this unbalanced data, it can get really biased and perform poorly when faced with a less frequent class. The good news is TensorFlow offers some clever ways to address this. We can use techniques like oversampling, creating artificial examples for the minority class, or undersampling, reducing the number of instances in the majority class. Another option is assigning different weights during training, making the model focus more on those rarer cases. And sometimes, ensemble methods are helpful too, building multiple models to give a more balanced perspective. Most importantly, don't just rely on accuracy. Use metrics like precision and recall to really understand how well your model is performing for all asterisk classes. Okay, let's talk about data augmentation in TensorFlow. It's a really important technique when you're working with smaller datasets. Basically, it's like creating slightly different versions of your existing images or data to artificially expand your training set. There are tons of ways to do this. Simple things like rotating and flipping images are common, but we can also get more complex with text augmentation, swapping out words or changing the order of sentences, for example. Audio data can be augmented too, by adding noise or shifting the pitch. TensorFlow provides tools to help with this process. Here it has a really handy image data generator which makes applying transformations super easy on the fly during training. And if you need more fine-grained control, TensorFlow's core image functions let you manipulate pixels directly using tensors. Okay, let's talk about the TF function decorator. It's a really important concept for optimizing your TensorFlow code. Think of it as a special instruction that tells TensorFlow to turn your Python function into a computational graph. This means TensorFlow can analyze asterisk how asterisk you're running the code and create an efficient plan, rather than interpreting it line by line in Python. This leads to some serious performance improvements because it reduces all those little overheads of running in Python. Plus, it makes automatic differentiation work seamlessly within that graph, a huge win if you're doing any kind of training or model building. It compiles your function into a graph and then executes that graph, which is significantly faster than running the original Python code. You can see a small example here to illustrate how it works. Okay, let's talk about custom layers in TensorFlow. They're super useful when you need something beyond what's built in. Basically, a custom layer is just a class that extends the base TF cures layers. Layer class. It's like building your own Lego brick for your neural network. Inside this class, we'll define the parameters our layer needs, things like weights and biases in the init method. Then, the build method is called when the layer receives its input shape, allowing us to create those parameters based on that size. Finally, the call method defines how the layer actually processes the input and produces an output. It's the forward pass. I've shown a simple example of a dense layer here, but you can build layers for almost anything. Don't forget to document your layer as well. Okay, let's talk about custom loss functions in TensorFlow. They're super useful when the built-in losses aren't quite right for your project. The basic idea is to create a function that calculates how well your model is performing, and it needs to be something TensorFlow can understand and use for training. You'll start by defining this loss function in Python, which takes the predicted outputs and the true labels as input. Then, you'll convert that into a TensorFlow operation using tf_py function. This allows TensorFlow to automatically calculate gradients during backpropagation. Finally, when you compile your model, be sure to pass your custom loss function to the compile method, and that's it. It's all about making sure TensorFlow can work with your specific needs. Okay, let's talk about TensorFlow Hub. It's a really handy resource for anyone building ML models. It's basically a library packed with pre-trained models that you can just plug into your projects. Instead of having to train everything from the ground up, which takes ages and lots of data, you can borrow these existing models. This massively speeds things up. It's all about reducing development time and making it easier to experiment with different approaches. Plus, there's a fantastic community aspect where you can even share your own trained models. Okay, let's talk about transfer learning in TensorFlow. It's a really clever way to boost your deep learning projects. Basically, we take advantage of models that have already learned a ton from huge datasets. Think of it like this: instead of building an image recognition system from scratch, you start with a model that already knows how to identify basic shapes and patterns in images. We freeze those initial layers, meaning we don't change their weight, so they keep doing their job of extracting useful features. Then, we add new layers on top specifically designed for your asterisk problem. Only these new layers get trained, which significantly speeds up the whole process and often leads to better results, especially if you're working with a limited amount of data. Let's talk about TensorFlow Lite. It's like a special, streamlined version of TensorFlow, built for running machine learning models on devices that aren't super powerful. Think your phone or even tiny microcontrollers. It's designed to be really small and efficient, so you can get those smart features working smoothly without draining the battery or slowing things down. It's used everywhere, from recognizing objects and photos on your smartphone to tracking your fitness goals with a smartwatch, all the way to controlling robots and automating factories. Basically, if you need machine learning on the edge, meaning directly asterisk on asterisk, the device TensorFlow Lite is a really popular choice. Let's talk about deploying your models. TensorFlow Serving is essentially the engine that gets your trained TensorFlow models out into the world and ready for action. It's like a delivery service that manages all the moving parts so your model can serve predictions efficiently. It handles different versions of your model, scales to handle lots of requests, and allows you to update your models without any downtime. Think about how fraud detection systems need to process transactions in real time, or how personalized recommendations are delivered. That's where TensorFlow serving really shines. Okay, let's talk about distributed training in TensorFlow. Basically, it's all about speeding things up when you're working with really big models or huge amounts of data. Instead of one machine doing all the heavy lifting, we break the work down and spread it across multiple devices, think GPU or even TPU. There are two main ways this works: data parallelism, where each device gets a little chunk of the data and calculates its own gradients, and then model parallelism, which is when you split the actual model itself across multiple devices. TensorFlow provides tools like mirrored strategy to help us manage this process pretty easily. It's a really powerful technique for tackling those massive training challenges. Okay, let's talk about training TensorFlow models with multiple GPU, really important technique for speeding up your deep learning workflows. Basically, what we're doing is scaling up our training process to handle much larger datasets and more complex models. The core idea is data parallelism. We split the data amongst several GPU. Each GPU gets its own copy of the model. Then, after processing each mini batch, those GPU independently calculate the gradients, how much they need to adjust their weights. But here's the key: these gradients are synchronized and combined across all the GPU before actually updating the model parameters. TensorFlow makes this easy with the TF distribute strategy API, offering strategies like mirrored strategy that replicate your model on each GPU. It's a powerful way to significantly reduce training time. Okay, let's talk about mirrored strategy. Basically, it's how TensorFlow handles training your models across multiple GPU or even TPU. Think of it as splitting up the work so you can train much faster. The strategy automatically divides your data between those devices, and each device gets a full copy of the model. Then, after processing a small chunk of data mini batch, all the devices calculate the gradients. That's how they learn, and then they synchronize those updates to make sure everyone's on the same page. It's like a team project where everyone needs to agree on the final result. It's super useful if you have a really big model or want to speed up your training process. Okay, let's talk about sigmoid and softmax. They sound similar, but they have very different roles. Sigmoid is a classic activation function that squeezes any input into the 0 to 1 range, making it perfect for predicting probabilities in binary classification scenarios, essentially asking, is this an example of class A? Now, softmax takes things a step further, especially when you're dealing with multiple classes. Instead of just giving you one probability, it creates a whole distributional list of probabilities representing how likely the input is to belong to each possible class, and these probabilities always add up to 1. So, if you have 3 classes, softmax will give you 3 numbers between 0 and 1 that tell you how likely the input is for each class. Okay, let's talk about how to handle different types of classification problems in TensorFlow. When we're dealing with multi-class classification, like identifying whether a picture is a cat, dog, or bird, each image can only belong to one category at a time. We use the softmax activation function and categorical cross-entropy loss to make sure our model outputs probabilities for each class, adding up to 1. Now, let's move on to multi-label classification. This is where things get interesting. Imagine an image that contains both a cat asterisk and asterisk a dog. It could belong to multiple categories simultaneously. To handle this, we use sigmoid activation on the output layer and binary cross-entropy loss. Each label gets its own probability, indicating whether or not the particular label is present in the sample. Does that make sense? Okay, so let's talk optimizers in TensorFlow. They're super important for getting your models to train effectively. We've got a few key players. First up is SGD, the original gradient descent method. It's really straightforward, but you often need to tweak its learning rate quite a bit. Then there's Adam, which is probably the most popular these days because it automatically adjusts learning rates for each parameter, making things much easier. RMSprop is another adaptive option that can be great when you have sparse data or noisy gradients. And finally, add a grid. This one also adapts learning rates but sometimes needs a lower overall learning rate to work well. Okay, let's talk about how TensorFlow handles mixed precision training. It's a really clever technique that can speed up your models and save memory. Essentially, TensorFlow intelligently switches between different numerical precisions during the training process. It starts with float 32 for most operations, but when using hardware like NVIDIA GPU with tensor cores, it will automatically switch to bfloat 16, which is a wider dynamic range format that's great for those cores. Then, if needed, it might use float 16 in certain parts of the calculations. The key thing is loss scaling. TensorFlow dynamically adjusts how much you scale your loss values during backpropagation. This prevents tiny gradients from causing problems and ensures everything stays stable. By doing this intelligently, you get faster training times, reduced memory usage, and a more efficient process overall. Okay, let's talk about how we can make our TensorFlow model smaller and faster. Two really important techniques are pruning and quantization. Pruning is like a gardener carefully trimming unnecessary branches from a tree. We identify the least impactful connections in the network and cut them off, essentially removing those weights. Quantization, on the other hand, is about reducing the size of the numbers representing our model's values. Instead of using large floating point numbers, we can represent them with smaller integers, which drastically cuts down memory usage and speeds up calculations, especially when running on devices like smartphones or embedded systems. Often these techniques are combined for even greater efficiency. It's a win-win. Let's talk about how the TensorFlow Model Optimization Toolkit makes your model smaller and faster. Basically, it's a set of tools that help you reduce the size of your trained neural networks without sacrificing too much accuracy. It does this through three main techniques: quantization, pruning, and distillation. Quantization lowers the precision of the numbers used in the model. Think turning 32-bit floating point into 8-bit integers, which shrinks the model's footprint and saves memory. Pruning identifies and removes unimportant connections within the network, making it sparser. And finally, distillation trains a smaller student model to learn from a larger, more complex teacher model. The toolkit provides easy ways to apply these optimizations during or after your training process, often taking advantage of hardware like GPU for speed. Let's talk about visualizing your TensorFlow models. TensorBoard is a fantastic tool that comes built in with TensorFlow, and it's really useful during training. Think of it like a dashboard for your model. It helps you see exactly what's happening under the hood. You can visualize the actual flow of data through your network using graphs, track metrics like loss and accuracy over time to identify trends and problem areas, and even display images or audio generated by your model if you're working with generative models. To get started, you simply need to enable TensorBoard in your TensorFlow session, log your metrics and summaries, and then launch TensorBoard from the command line, pointing it to the directory where your logs are stored. Okay, let's talk about the big shifts between TensorFlow 1x and 2x. Back in 1x, everything was built around a static graph. You define the whole computation ahead of time, which could be a bit tricky to manage if your model needed to change dynamically. But 2x changed things completely with eager execution, where operations happen as you call them, making debugging and trying out new ideas way simpler. Plus, Keras is now built right in, providing a much more user-friendly way to create models. And instead of managing variables separately, 2x uses variables directly for things like model weights. It just feels more natural. The automatic differentiation also got a significant boost. Okay, let's talk about learning rate schedules in TensorFlow. Consistent learning rate can sometimes be a problem. It might cause your model to bounce around and not converge effectively. Learning rate schedules are designed to address this by dynamically adjusting the learning rate during training. You've got options like step decay, where you reduce the rate after a set number of steps, exponential decay, which steadily lowers it over time, polynomial decay offering more nuanced control, or even cosine annealing, which mimics a cosine wave for smoother adjustments. I'll show you a quick example using step decay in Python to illustrate how to implement this within your TensorFlow model. Remember to choose the schedule that best suits your specific problem and model. Okay, let's talk about custom metrics in TensorFlow. Essentially, they give you the power to define what good looks like for your model beyond standard measures. Think of it like this: accuracy is great, but if you're building a fraud detection system, precision and recall are far more important. To create one, you use the TF-Keras metrics API. You define a class that inherits from metric, initialize any variables you need to track, implement an update state method to handle each training step, and finally, an result method to calculate the final metric value. It's really not as complicated as it sounds. Okay, let's talk about dropout regularization. Think of it as a way to train your neural networks to be more resilient and less likely to memorize the training data. Basically, during each pass through the network, we randomly turn off some neurons, like temporarily removing them from the equation. This forces the remaining neurons to learn more general features instead of relying on specific connections, which helps prevent overfitting and boost performance when applied to new, unseen data. In TensorFlow, it's as easy as adding a dropout layer in your model with a specified dropout rate. Okay, let's talk about batch normalization in TensorFlow, a really important concept for getting your models to train well. We'll start by using the Keras layer's batch normalization layer, which is our go-to tool for this. You'll want to pay attention to arguments like axis, which usually indicates whether you are working with feature vectors or images, and momentum, which controls how quickly it adapts. A small epsilon value is also important. It helps prevent division by zero. Using batch normalization can really stabilize your training process and often leads to better results. As a quick example, you'd wrap a dense layer with batch normalization followed by ReLU and dropout. Okay, let's talk about activation functions. These are like little decision makers inside each neuron of a neural network. They add a layer of nonlinearity, which is essential for learning complex patterns. Think of them as switches. They decide whether or not to pass the signal along based on the input they receive. We've got some popular ones: ReLU, which is really simple and fast; sigmoid, which outputs values between 0 and 1, great for probabilities; tan, similar to sigmoid but centered around 0; and softmax, used at the end of classification problems to give us a probability distribution over different classes. TensorFlow makes using these functions super easy. Just import the TFNN module and call the function with your input. It's important to pick the right activation for your specific problem. Okay, let's talk about sequential and functional models in TensorFlow. Sequential models are really easy to use. They're great for straightforward tasks where the order of operations is important. Think of it like a chain reaction, layer by layer. Then we have functional models, which give you much more flexibility, especially when building complex architectures like ResNets or inception networks. They let you define the entire model as a collection of functions, making it easier to reuse components and create really intricate designs. The main difference is that sequential models are simpler but less adaptable. Okay, so you've trained your model and it's doing great. But a model by itself isn't very useful. The next big step is getting it out there, deploying it to an application that people can actually use. There are several ways to do this. One popular option is using serverless functions like Google Cloud Functions or AWS Lambda, which are perfect for handling occasional requests and automatically scaling up as needed. You could also integrate TensorFlow serving into web frameworks such as Flask or Django to build simple API. If you're building a mobile app, TensorFlow Lite allows you to run your model directly on the device, providing speed and keeping data private. Finally, containerization with Docker is a good way to package everything up so it runs consistently across different environments. Okay, let's dive into a common TensorFlow interview question: understanding the difference between static and dynamic computational graphs. A static graph is like creating a detailed blueprint for your calculations before you start building anything. This allows TensorFlow to optimize it for speed and efficiency. It's also very predictable. If you run it again with the same inputs, you'll get the same result. Dynamic graphs, on the other hand, are built as you go, like writing code that executes step by step. They offer a lot of flexibility, which is really useful for models where the structure changes, such as recurrent neural networks. However, they can be slower because TensorFlow has to build the graph during runtime. Let's look at some simple examples of how these graphs are created in Python and see how they differ. Okay, let's talk about debugging TensorFlow models. It's a really important skill. You don't want your model crashing or producing strange results. TensorBoard is honestly your go-to tool here. It lets you visualize everything from the graph of your model to how things are going during training, like accuracy and loss. Then, logging key variables and operations with TensorFlow's summary functions can help you track what's happening step by step. You also need to watch out for gradient issues. Vanishing or exploding gradients can cause instability. And don't forget checkpoints. Saving your model regularly gives you a way back if things go south. Finally, when debugging complex models, it's often helpful to break them down into smaller pieces and test each part individually. Okay, let's talk about how to really get your TensorFlow models performing at their best. It's rarely set it and forget it situation. First off, make sure you're handling your data well, cleaning it up, scaling it appropriately, and thinking about ways to boost the size of your training set through techniques like data augmentation. Then, don't be afraid to experiment with different hyperparameters. Things like learning rates and batch sizes can have a huge impact. Choosing the right model architecture for the job is also vital. Consider using pre-trained models as a starting point if that makes sense. And finally, look at regularization techniques. They help your model generalize better and avoid getting stuck in local minima. Thank you for watching.